Hello everyone, I am Bharat Singla and welcome to our channel Learn Competitive Programming with CodeChef. If you desperately want to master competitive programming and get your hands dirty in data structures and algorithms, then this is a one-stop destination for you. Every week, we upload problem explanations from CodeChef's contests. We also upload conceptual videos on various programming paradigms and conduct live problem solving sessions. Yes, live interactive sessions. So before we begin, here's a reminder for you to hit that subscribe button if you haven't yet already. Great! Now that you have subscribed, let's get started. So today we are going to discuss a very interesting problem from CodeChef's November Long Challenge 2020, and the problem code is restore. And why I make that statement is because the problem is subjective. There are multiple different ways to solve the question and multiple approaches. Today we are going to discuss one of them, which is not the only way to solve the question, but is an approach which works. The difficulty level is easy, medium. There are none prerequisites. Basically, I'm going to explain everything that you need to solve the question. So let us discuss today's agenda. So first, as usual, we are going to do the explanation of the problem statement, then understand the concept required to solve the problem, and then do a walkthrough of the pseudocode as well as the implementation. So without any further ado, let's get started. But before we begin, do you guys know that CodeChef also conducts free live sessions on Unacademy where we try to teach every possible topic related to competitive programming? We have list of courses for all skill levels, such as beginner courses like Introduction to Programming in C++ and Java, intermediate courses like courses on recursion, number theory, basic data structures, etc., as well as advanced courses on topics like dynamic programming, graph theory, segment trees, and many more. Here, you will be taught by top coding experts who are IUI medalists, ICPC World finalists, and have worked at companies like Google, Facebook, Flipkart, LinkedIn, and basically all those tech giants. All you have to do is download the Unacademy app or register yourself at unacademy.com by clicking this button Start Learning here and choosing your goal as competitive programming. But this isn't just it, guys. You can also go for the Plus subscription where you get additional benefits as well as full time doubt solving and individual support. You also get the access to solve the problem sets curated by these top coding experts for each topic. And to add the icing to the cake, the mentors who are going to resolve all your queries are 6-star and 7-star coders as well. So subscribe to An Academy Plus. Don't miss this golden opportunity of learning from the best in the world and kickstart your competitive programming journey today. You can also use the code Bharat27 and get an instant 10% discount on your subscription. So don't forget to use the code and hurry up guys, subscribe to An Academy Plus. So let us start off with a problem statement. So it is saying that Alice has a very complex machine which when fed with a sequence A produces a sequence B of the same length where for each valid I, Bi is said to be the largest index J such that Aj is a multiple of Ai. So what does it exactly mean by this? So let us take an example. Here I have taken this array A which is given in the sample input as well. So let us try to figure out the corresponding B. So let's say this is B, right? So we are going to take every element that is basically 2, 6, 5, 3 and 4 and then we are going to traverse from the right so that we get the largest index J. And what we are going to do is that whenever we encounter the element to be a multiple of this element, so there we are going to break and we are going to take the index and set Bi to that index. So for example, for 2, the rightmost element is 4 and the index of 4 is 5. Here we are talking about the one based indexing. So after 5 for 6, what's the rightmost element? Yes, you guessed it right. It is 6 itself. A number is a multiple of itself, right? And its index is 2. The same goes for 5 as well. The index is 3. And for 3 also, there's no element in the right which is a multiple. But 3 is a multiple of itself. So the rightmost index turns out to be the index of 3 which is 4. And for 4 also, the index of 4. So here we have this array B and you can verify that we have built it correctly, right? So now what we are given is that Alice has given you a sequence B that was produced by the machine. We have to find a sequence A such that when it is fed into that machine, the machine produces B. So now we have basically reversed the process. We do not want to find the corresponding B. Instead, we want to find an array A such that when it is fed into the machine, it gives us B. Right? So what now? There are some observations that we can make. So first, let me define this function. So if I define this function f of A, which is going to give us an array B. So you can take this f to be the machine, right? Which is taking in a sequence and returning out a sequence. Now here in the problem statement, we'll be given B and we have to find any array A such that f of A equal to B, right? So what are a few observations that you can make? So the first observation is that for A, there exists, so there exists only one B, right? And this can be easily proven as well. We are building up the array B using the elements of A. So there has to be only one B. And also this can be said in other words as well, that since we have defined a function f for the machine, so a function should only take one input and return one output, right? So for one A, there should only be one B. But is it true the vice versa? Just you can pause the video here, but just brainstorm about it. So no, it's not true. So for B, there can exist multiple A's. So for one array B, there can exist multiple A's. But as long as we are printing one of them, which works, that is, if it is fed into the machine, we are getting the B which we wanted, which was given in the input. So as long as the A we are printing is correct, we can print any one of them. We do not need to print all of them. Any one A which is correct will give us an AC. Now, why? So let us take up a few examples for this as well to just prove these two observations above. So let's say I take this sequence. So A I take to be, let's say 5, 6 and 7. So this is a small array A, and what will be the corresponding array B? It will be okay. So we again iterate from the right for each element. So for 5, what's the rightmost index? It is 1, the number itself. So we set 1 here. For 6, it is 2, again the index of the number itself, because there isn't any multiple in the right. And for 7 also, the index itself. So this is the corresponding B for A. So we have seen this clearly that for 1A, we can only get 1B. We cannot set it to be 4 or 12 or something like that, right? There has to be only 1B. But it is not true the vice versa, right? That's what we have written here. So let us take another A which should give the same B. So what could be 1A? It could be, let's say A2. I take to be 10, then 11 and 12. Is it giving the same array B? Yes, it is. For 10, the rightmost element is 10, so 1. For 11, there's 2. And for 12, it is 3. So here we have two arrays, A1 and A2, both of which are giving us the same B. So we have proved these two observations above. So now let us think of the third observation we can make. Now this is also pretty straightforward, that for each I, that is basically for each index B of I, where B is the input we are given, the array B has to be greater than or equal to I. Now again, we are in the whole problem, we are going to talk one based indexing. So why is this true? Again, let me take this example here. So for A2, even though we did not find any element in the right for each element here, but still the element itself will always divide itself, right? A number is a multiple of itself. So the rightmost index has to be at least the index of the element itself. So for B of I, whenever we are given the input, it will be taken care that B of I is always greater than or equal to I. Otherwise, this array B is not valid, right? This condition should be met, and we do not have to take care of this. The person who has designed the test cases, he has taken care of this already, but this is a good observation to start off. So now let me just take another example of 1A and you try to figure out the corresponding B, and this time I'm going to take A to be very big, so a lot of elements in it. So let's say we have this array A. So let us try to figure out the corresponding B. I have also punched in the indices here, and just let's start building B. So for 2, which is the rightmost element? Yes, it is 40 and its index is 8. So the first element in B is 8. For 10, which is the rightmost element? Again it's 40, its index is 8 again. So for 15, what's the rightmost element? There's no multiple, it's the number itself. So 3. Now again note that we are following the third observation here, this observation again, because even though we could not find any multiple, we are going to inevitably stop at that element at least, right? So this has to be equal to if there is no multiple in the right, or greater than if we find any multiple. So 3 here. For 20, again 40 is the rightmost element, its index is 8. So 8 here. For 27, there's no multiple in the right, so 5, the index itself. For 9, yes, there is a multiple 18, its index is 7. For 18, no multiple, index again 7. And for 40, the last element does not have any multiple in the right, so it has to be the index of the last element itself. So here we have this array B, which corresponds to this array A. So now that you have gotten to grips with this, how this is all working and how f of A is returning B. So now let's try to reverse the process. Let us talk about one valid B and try to figure out a corresponding A for it. Again, there could be many array A's, but we are just talking about one of them. So if I take this array B to be 5, 2, 3, 4, 5, and some of you might have noticed that this is the same as given in the problem statement as well as the sample input. So let us try to figure out one A for it. Okay, so first we can assign any arbitrary number here. This is just the random number, right? We do not need to take care of the first number. Instead, we just have to take care that we are forming the correct multiples and the correct factors. So this is 10, and if this is the array, fine. So if this is the array given, I only want this number to be a multiple of the first number, right? So the fifth number should be a multiple of the first number. So let's say I take it to be 50. So for the second number, we have to be much more careful. Why? Because we do not want any of the numbers in the right to be a multiple of this number. Otherwise, let's say if this was a multiple of this number that we are going to assign here, then instead of 2, we would have been given 5. Or if this was a multiple, then instead of 2, we would have been given 4. So we have to make sure that there does not exist any multiple of this number in its right. So, okay, so if I take it to be 20, right? For now, there's no clash, right? 50 is not a multiple of 20. For 3 again, we have to make sure that the same for 20 as well. So there should not be any multiple in the right. So I can take it to be 30, fine. And for 4 also, I can take it to be 40. There isn't any multiple in the right. And for now, it looks correct. But again, let's try to reverse the process. Have we built the array correctly? Okay, so now that we have this array A, let's try to find the array B. So for 10, the rightmost element is 50 and the index is 5. We have 5, so we are fine till now. For 20, what's the rightmost element? Oh, it's 40 and its index is 4, but here we have 2. So we have messed it up even though we took utmost care here. So what was the issue here? So the problem was that even though at every step we were taking care for the future, but we somehow forget what we had done in the past. So here we set 40 based on the elements on its right. We took utmost care that no element in its right should be a multiple of 40. This is what we took care. But what happened was that somehow we forgot to take care for the elements on its left. We also wanted 40 not to be a multiple of 20, right? But this is not what we end up with. We ended up with 20 being a factor of 40, and this is what made our array A incorrect. So what can we do now? Instead of 40, can we choose some elements wisely so that we do not need to take care of the elements on its left as well as on its right? Because if we do so, the complexity would rise up to n square. So we need to choose 40 wisely such that there is no conflict. And why only 40? We could take this care for every element, right? Why not choose every element smartly such that in the end it guarantees us no conflicts? So instead of 40, let us choose the number a little wisely. And how? Let's discuss that as well. So, how can we go about this now? So, instead of just telling you the correct solution, I want you to build that intuition of how you can come up to the solution. So, here what you can do is that, okay, so I am ending up in a clash if I just assign numbers randomly. So, what can I do to prevent this clash of factors and multiples? Here, there's a good chance that you would have clicked that, okay, I can use prime numbers here. Now, why prime numbers? Because prime numbers do not have any factors. So basically, there's a very less chance that you will end up in a clash. Or in fact, there's a 0% chance that you will end up in a clash. And an added benefit that prime numbers give, except for the benefit that they do not have any factors, is that a prime number is never a multiple of another prime number, right? This is similar to the first fact, but this is a great observation, right? This is something that will help us go very close to the solution. So what we can do is that instead of just assigning numbers randomly, we can assign prime numbers here. And whenever we want a number to be a multiple of another, we could set it to its square, or we could set it to 2 times that prime number, right? This way, we are only building up multiples of a number when we want to. We are not accidentally getting a number to be a multiple of another. So let's take up the example again. This was B, and now let's try to figure out A for it. But this time we are going to use prime numbers. So what can we do is we can first assign 2. 2 is a prime number, and there should not be any confusion why we have taken 2 here, right? 2 is the smallest prime number and it is a prime number as well. So 2 is fine for the first number. Then if this is the array, so if this is the array, then what we can do is that we want this number to be a multiple of this number, right? That's what 5 denotes here. So what can we do is we can again assign 2 here. Now why? Because 2 is a multiple of itself, right? We could have set it to something like 4 also or 8 also, but 2 is a multiple of itself. And this is again helping us in keeping prime numbers in the array, right? Because if a multiple of 2 is being taken, like 4 or 6 or 8, then it is not a prime number. And again, we could have ended up in a clash. So taking 2 is best, right? It is a multiple as well. And since it is equal to the number here, and we have taken prime number here, so it is also a prime number. For 2, we do not want it to be a factor of any of the numbers in the right. So what we can do is we can simply assign 3 here. For 3, again, we could simply assign the third prime number, which is 5. For 4, the fourth prime number, which is 7. And boom, here we have this array A, right? And hopefully this should be correct. Let us again backward calculate and verify. For 2, the rightmost element is 2. Its index is 5. For 3, there isn't any multiple. So we can write 2 here because the index of 3 is 2. For 5, again the index would be 3. For 7, the index would be 4. And for 2, for the rightmost element, here it has to be the basically the length of the array. That is the index of this element. So here 5. So boom, we have this solution here with us, which works perfectly, and we did not end up in any kind of a clash because we use this smart set of infinite numbers called the prime numbers, right? So now let us take another example. So now let us take up this array B that contains 1, 4, 3, 4, and 5, and this time we are going to build array A in such a way that how the code would build it. So now we are going into a little bit of algorithmic thinking. So for the first element, we can always assign 2. Now why 2? Because 2 is a prime number and it's also the smallest prime number. So it basically gives us a good consistency. We could have also written 3 here. So 3 would have also worked, or 5 would have also worked because they are also prime. But starting with 2 is always beneficial since it's the smallest prime number. So we'll start with 2 and then we are going to move forward. Now 4, then we can simply assign the second prime number. For the third position also the third prime number, which is 5. Now here we are seeing 4 and we have seen 4 earlier as well here. So what we are going to do is we are going to again set it to the value that we had set earlier. So here we are going to set it to 3. Now why? Why does it work? So let us say that okay, instead of 4 here it was given 5. So in B, instead of 4 here we were given 5. So what would happen? I'll try to prove that why this b is not possible if here instead of 4 we were given 5. So note, so let us take this to be a, and this number to be b, and this number to be c. So what 4 here denotes that this number should be a factor of the fourth number in array A, right? This number here should be a factor of the fourth number, and this is what 4 here denotes. So for now we are taking it to be 5. So this is 5 for now. So 4 should be a factor of the fifth number, right? This element here should be a factor of the fifth number, and this element here, which would be in the fourth position in A, should be a factor of the fifth number, right? But now carefully observe that we also want this number not to be a factor of this number. Otherwise here the rightmost index would have become 5. It would have been turned into 5 because then it was the rightmost element. So we want A to be a factor of B. We want B to be a factor of C. But we don't want A to be a factor of C. Right? This is not mathematically possible. So what this basically tells is that for whenever we are encountering 4 here or any number which is not I, so here it is not 2, right? The index here was 2 in B, but it is 4. So basically it wants us to make an element in its right to be a multiple of this number. So what this basically guarantees, our observation here, is that here it has to be 4. It has to be the same number again. Why? Because it cannot be less than I. B of I can never be less than I. This is what we have already discussed. And it cannot be greater than I as well. Because then, if it was, let's say, something like J, which was not I, so here we would have been given J because that was the rightmost index now. So here we will always be given the same number again. Fine. So this should be clear till now. And let me just bring it back to its original state. So this was B, and this is what we have concluded, that we'll always be given the same number again if we have already seen it here. So we can write 3 here, then we can write 5, and again we are going to set it to the same value that we had set earlier. And we do not need to make it something like 3 square or 3 into 2. A number is a multiple of itself, we all know that. So we can simply assign 3 here. We could have also assigned 9 or 18 or 6 or something like that, but it is always beneficial to assign the same number again. And this can be easily clarified as well. It is always beneficial to take the same number again instead of taking a multiple, because then we are ensuring that we only have prime numbers in the array. If we take 6 here or 9 here or 12 here, then this is not prime number, and there's a high chance that we could have ended up in a clash. So it's always beneficial to only keep prime numbers in the array, so that there is a less chance that we indirectly or accidentally end up with factors and multiples that we do not want. So let's keep 3 here. Then we have C5, then we see 5. So for 5 we can assign a new prime number because we haven't seen it already. And here we assign 7 or 11 or anything like that. And here we go. We have this array A much more systematically built now. So this is how we can build A. And now let us move on to the pseudocode. So let us have a look at the pseudocode as well. So first we are going to take two inputs, n and b, where n is the length and b is the array we want the output to be. Then we are going to define an array A of the length n. This is going to be our final output, the array A, the answer. Then also we are going to define another variable d, which is going to be a dictionary or some sort of a mapping, which will map elements of b to a prime number that we have assigned earlier. Then we are going to iterate I, a variable I, that will go from 0 to n minus 1. Fine. Then just defining this variable elim is equal to b of I, so that we are dealing with elements instead of index. Then we are going to check if element is in dictionary.keys. That is basically if we have seen the element before, in that case we have to assign a multiple of the prime we set earlier in the array A, right? So we are going to set a of I equal to d of elim. Fine. This line basically what it does is that it is a simple memoization technique, that whenever we have assigned some value, so we are just going to store that, and whenever we need it, we are going to take it back from the dictionary. So this will just map the elements of B to a prime number that we had already assigned when we first saw this element. Fine. And why we are doing this? Because we want it to be a multiple. Here we could have also done the square of d of lim or 2 times d of lim, but d of lim also works, right? We all know that a number is a multiple of itself. And in the else condition, that is basically we are seeing this element for the first time. If it is not seen yet, then we are just going to assign d of lim equal to the ith prime number, right? That is what we want. And we are going to store it in D so that whenever we need it in future, we can retrieve the value. And also we are going to set a of I equal to the ith prime number. Fine. Or since we have computed it above, we could simply set it to D of Ln. Finally, after all those iterations, after I goes from 0 to n minus 1, we are going to print A. Fine. So this is how the pseudocode goes. Now, before we move on to the implementation, I just want to tell you about the fastest way to find the ith prime number. And this way works very well, especially when you have to find the ith prime number multiple times. So you can say that whenever we have a lot of queries that we have to answer, where a query is of the form to find the ith prime number or jth prime number, then what we can do is we can use this algorithm. The algorithm is almost O of n, and it was devised by this man Eratosthenes. You may have heard of him, and the algorithm is called the sieve of Eratosthenes. So although it's a very standard algorithm, so I won't be explaining it in very detail, but there's one animation I want to show you that if you are really starting out with this algorithm, then it could help you that how this algorithm works. So here is how it goes. So first is going to take 2, and then it's going to cross out all the multiples of 2 from this list, because we know that they cannot be prime numbers since they have a factor 2. Then we are going to do the same for 3 as well, going to cut down all its multiple. Then for 5 also, striking off every multiple of 5. Then for 7 also, going on and crossing out all the multiples. And finally, we'll be left with only the prime numbers. Now why? Because we have strike down all the numbers who had some factors. So in the end, if a number is not striked out, basically it did not have any factor. So these are the final numbers. So this is how the sieve of Eratosthenes algorithm works. Now let us move on to the implementation. The implementation is going to be in Python, guys. So here's the code for the problem. Firstly, we are going to define this function sieve of Eratosthenes. It's a very standard algorithm. So I won't be spending a lot of time on this. You can find this algorithm anywhere on the net. And after defining this function, we are just going to assign this list to a name primes. So this will basically contain all the prime numbers from the range 2 to 4 into 10 to the power 6. And why 4 into 10 to the power 6? Because remember that in the problem statement we were given that the integers in A had to be less than this. So this is just a arbitrary large value. So it works and it's not very large as well. Fine. Then we are going to take the input for test cases and run this loop to test cases time. So then we are going to take an integer input as well as array input. Also, we are going to define two variables answer that will initially contain 0 n times and dic standing for a dictionary. Fine. Then again we are, as we saw in the pseudocode, we are going to iterate the variable I from 0 to n minus 1 and set lim is equal to arr of I. Now if lim is in dictionary, basically we have already seen this value. So we are going to retrieve the value that we previously assigned and set answer of I equal to this value. Else we are going to set answer of I equal to the ith prime number. Basically this primes variable contains a list of the prime numbers. So primes of I is essentially the ith prime number. Then we are going to also store it in dictionary, and that's how you do it. Dic of lim is equal to answer of I. Fine. Finally, after all those iterations and computations, we are going to print this answer, but we do not want those square brackets, right? We only want the values to be space separated. So in Python, you could use this star notation and it just yields all the values separated by a space. So this is how the code goes, and let's try to submit it now. So here I have pasted the code, and now let's hit the submit button. So yes, we have got an AC, a correct answer, and this was basically it. Now, before we leave, I want you to write down in the comment section the sieve of Eratosthenes algorithm's complexity, the time complexity of this algorithm. Although we all know it is close to O of n, but still I want you to write the exact complexity, and also if you know where that complexity came from, that is basically the derivation of all those mathematics, then please write that down in the comment section.